So first of all, thank you everyone for coming. And so it's my first time here. So if I made any mistake, please stop and correct me in between. And also, I prepared it in a very short amount of time. So uh, I'll be looking in that reference sometime. Hope you don't mind that. Yeah. So in my masters, I did a project about this particular galaxy called UGC 12591. Our question was how do massive galaxies evolve over time? And UGC 12591 is a very interesting object to work on because you can see it's massive in size, at least 3 times in physical dimension than our Milky Way, and probably at least 10 times in mass than our Milky Way. So it's massive, and it has a very high rotational velocity, around twice that of Milky Way, about 500 kilometer per second. So massive in size, very high rotational velocity, and it's located around in a very isolated environment. So what kind of interaction is going on with the surroundings is a important question to answer. And I think the nearest galaxy to that object is around 2 megaparsec away. So what kind of, sorry? Okay. How to, okay, all right. So what I am telling is what kind of interaction with its surroundings have affected its evolution over the redshift is a important question to answer. So we focused on that specifically, and a lot of other things came into a like star formation rate, black hole growth, and etc. So all of that had major contribution to the galaxy's evolution over the redshift. So previously, we didn't know the structure of the galaxy, what are the physical dimension. We from the this is tricolor image of the galaxy. You can from the image you can see it's kind of a lenticular galaxy with a bulge. So almost nothing specific about the structural parameters was known for the galaxy. Very scattered work was done before that, like in I think in 1986, Giovanelli find out the galaxy and find out the rotation velocity of the galaxy. I think up to 30 kpc or so from HI 21 centimeter. And after that, I think someone in 2012 they found some massive galactic halo from XMM Newton X-ray soft X-ray observation. So not much was done about the galaxy, and we didn't know specifically the structure of the galaxy. So I don't know why it was not done, because Georgiev, the guy who actually proposed the proposal in HST in 2013, their focus was on studying the globular clusters and their metallicity, and probably the to guess on early history of the universe connecting from that globular clusters. But his goal was not to know the structure of the galaxy, so we take it on. And it's very surprising, given that a quality of the HST data was available in the public domain. It's very deep view, so wanted to know the structure of the galaxy. So you can see the color picture here is at redshift 0.023, a similar bar type galaxy here around the same redshift. We don't know what it is. Blessons are told to look for catalog, so I searched for it and it showed that it's an infrared source. So other than that, we don't know anything up till now. So you can see that there are huge dust lanes around the galaxy surrounding the bulge in the center. And from the redshift, you can calculate the distance. Its local galaxy around 95 megaparsec away. It's a Hubble deep view. So some problem with it's an edge on view. We're seeing from the edge, not face on. So there are some problem with that. So it's a representative picture of our Milky Way. You can see that from face on view, you can see clearly the spiral arms you can see. But if the galaxy has a bulge, probably you may not see that more clearly. But in edge on view, you can see the bulge, but not the spiral arms. So some fundamentals here. Bulge and disks. This is called central spheroidal shape bulge of a galaxy, which has a different gravitation into it. Like it is a dispersion supported system. Stars can rotate in all direction at the same time on average, but in a disk, majority of the stars follow the same path. So here there is a disadvantage that we cannot infer that whether the galaxy has spiral arms or not, but we can infer about their bulge. So it was classified morphologically by Giovanelli as lenticular kind of hybrid S0SO object. So in general, lenticular object can be decomposed into bulge, central spheroid, and a disk, surrounding disk, and maybe a compact bright center. So we did, our aim was to decompose the different components of the system. So for the bulge, we modeled it by Sarsic function. We don't know why it exists, but it exists empirically. There is no theoretical base for that. And disk with exponential function, and there are some in the residue. We noticed that there are some leftover light which could be later modeled by a point spread function, which is generally takes the shape of Gaussian or Moffat, whatever. Okay. So we had data in 3-band VIH in optical data. So in the this is infrared, and this is kind of ultraviolet visible range, these two, and this is infrared. So we had 3-band data available, so we could kind of see how the parameters are changing with the change of the wavelength. So from that we can draw some inference also. Okay. So these are some important parameters, like we got Sarsic index as 2.32 to 6.38. In infrared, it gave us 3.68. Like classical bulges, generally we have in elliptical galaxies that are generally described by classical bulge of around 4, and those galaxies which doesn't have much spheroidal bulge are generally called pseudo bulge, which is for which Sarsic index is less than 2. So our system is hugely bulge dominated, and you can see the H band bulge to disk luminosity ratio is 69%, and if you take H band and if you consider the luminosity that is coming out from the bulge and luminosity that is coming out from the total galaxy, 41% of the flux is coming out from the bulge. So it's a hugely bulge dominated system. So what kind of physical processes has given rise this kind of bulge is an important question to answer. I think so. Okay. So these are some models. This is the galaxy, and these are the models, because you cannot directly evaluate some physical parameters looking at the data. You need to model it, replicate it, and depending on the residue, you can tell how good or bad the model is. So we have used Galfit for modeling the data. This is in ultraviolet, I think F814, and this is in H band. So you can see in UV there are a lot of dust lanes here, but in infrared there is no dust lanes. That means the UV light is absorbed somehow by the dust and emitted in the infrared region. That is why we can see the dust lanes properly in the UV and not see the dust lanes in the infrared. So these are the light profiles, like how light flux varies as a radius of the galaxy or semi-major axis, whatever you want to call, as a function of radius. Okay. These are the this is the data and this is the resultant model, and this is the Sarsic function, this is the exponential function, and this is the PSF. So you can see that the resultant model is highly dominated by the Sarsic function, which is used for sweeping the bulge. That means the overall light profile that is coming out of the galaxy is hugely dominated by the bulge. So it's a hugely bulge dominated galaxy. We don't know why, but it has a huge effect on its evolution. You can also see as we increase the wavelength, this is infrared, this is ultraviolet visual range. So wavelength is increasing in that direction. So you can see the um, effective bulge length is also increasing. That means bulge gets bigger as we go towards the higher wavelengths. That means the bulge is probably occupied by older stars that is emitting in higher wavelengths. Yeah. Okay. Now, what kind of effect of that bulge has in the star formation of the galaxy is an interesting thing to know, because we estimated the star formation rate to be around 0.1 to 0.6 solar mass per year from various methods, because different bands generally tend to give different star formation rate of different area, different time scale and different regions. So, for example, Galaxy XUV, FUV shows us recent star formation rate around 100 million years or 200 million years. And ACD generally takes into account the integrated approach, taking into account whatever number of band you have considered during the ACD fitting. So we can get fairly an estimate of constraint on the star formation, and you can see it's extremely low for such a massive galaxy. We'll come that later. So different bands show different age group of stars, may not be coherent always, but it more or less provides us with some constraint on star formation. So what kind of processes have triggered this kind of low star formation is very important. It's a galaxy view. I think it's NUV, which shows, I think, star formation from 200 million years of age. And you can see this is absolutely nothing is there, most probably like very faint. No significant young stellar population is there. But I think UVIT observation of that galaxy was proposed, but somehow it was not observed. We estimated the old stellar mass ratio of old stellar mass to young stellar mass as high as of the order of 10 to the 5. So nothing recent young star formation is going on in the galaxy. So here we have shown some comparison of the of our galaxy with some other massive galaxies and main sequence galaxies. Like those who are from stellar astrophysics probably know the HR diagram. Like in the main sequence, there are luminosity is proportional to some temperature to the some constant probably, and as time goes by, the stars will be probably go in maybe become supergiant or may become dwarf or something. So here you can see also this line is the main sequence galaxies for which star formation is proportional to stellar mass to the something constant. So, and this UGC 12591 falls in the region of fully retired or nearly retired galaxies. There is no star formation is going on. Also, there are some other galaxies like this galaxy, like Professor Bakshi is working on that J234504449. This galaxy has a huge jet that we don't see in UGC 12591, but their end goal is same. There are no star forming galaxies. So that could be an interesting thing to study, like how with time these galaxies deviate from the main sequence relation, like we do in case of stars also. So I think you can see that. We estimated the galaxy is quiescent passive for at least past 100 million years. Like we estimated the star formation rate averaging out for 100 million years, and there is no fluctuation, and it's more or less same with the instantaneous star formation that is coming out of the spectral energy distribution of the galaxy. And this is color diagram that because this I have not done in the paper, but referee was asking why the star formation is very low, so we have to convince him, because that is why we showed him that in the plotting in the color diagram also, because same color might not give result of precise result all the time. So if you can manage the color diagram, probably it is slightly better. So UGC 12591 here comes in the highly quenched galaxies, early type galaxies. These blues are late type galaxies that are still forming stars efficiently, and these are early type galaxies that are not forming stars efficiently. So this comes in between. So it's not fully quenched, but it's going in that direction. Okay. So hot process are got, sorry. Yeah, yeah. I think it's also classified as hybrid, which is in between early type and late type. So probably that might be the reason, but yeah, yeah. Yes, yes, yeah. Yeah, yeah, yeah. Yeah. Yeah, 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 yeah. 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 Yes, yes, yes. I think I'm analyzing some other galaxies which has UVIT data. So probably the same kind of thing. Yeah. Yeah, yes, yes. Okay. Yeah. Yeah, that's right. So these are the major processes by which star formation quenching can happen in a massive galaxy. Basically, the simple concept is no gas, no stars. So the thing is, stars, and I think for star formation, I think the temperature in the neighboring cloud should be around 10 to 30 Kelvin, and the like the gas are coming out from the halo, and their temperature, how the cooling rate is required for to come down and condensed in that temperature is also important. So we think from our analysis that morphological quenching is a major part of the quenching process, and bar quenching, we don't know there is a bar or not. Asian feedback is one of the thing, and mergers also. So before going into like how black holes can affect the star formation by its activity, there is something called like we estimated the black hole mass of the galaxy is supermassive of the order of 10 to the 8, but we don't see any like large scale radio jet or faint radio robes. We don't see anything of that. So the black hole is probably quiescent at there is no accretion probably, but mode of accretion probably is different. The black hole probably has grown in the past, and consequent AGN activity in the past probably that had affected the star formation in the galaxy, because when gas and jets come out of the AGN, it probably hits the circumgalactic halo, and it takes some time for the gas to condense and come out in the gravitational potential well of the disk and form stars there. So AGN could play an important role in that, in quenching the star formation also. But how much it is effective, we don't know uh, till now. So major possible contributors for the low SFR is morphological quenching is one of them. Morphological quenching is like if you have like growth of bulge in the center of the galaxy. For star formation, you need gravitational instability. Like that is when the gravity, like the in the cloud, there could be collapse, gravitational collapse, and you can form stars. So there needs some gravitational instability. But if there is a in the center, if there is a more massive object bulge, so that gravitational instability can be eliminated, which can reduce the star formation also. So this galaxy has a huge bulge, so morphological quenching I think is a suitable candidate which suppress the star formation in the galaxy. So past Asian activity also could be a possibly played a role. Like from the spectral energy distribution, we find that the galaxy recently the galaxy doesn't have much of its Asian activity, but in the for at least 10 to 8 years we found that. But before, like from the supermassive black hole growth, we can assume that it must have gone through some accretion process and violent jets and all that. That that is under consideration, and like yeah. So sometimes there are two kind of AGN feedbacks are there, like positive feedback and negative feedback. Positive feedback generally compresses the cloud gas in the disk, and it can positively affect the star formation, where star formation may get accelerated. And probably we are seeing here negative feedback, which is blowing out gas from the disk out to the galactic halo and increasing its temperature, which is taking time to settle down and condense. That is why, like we are seeing for recent years, we are not able to see much of the recent star formation. Probably after some time the gas is condensed enough, we may see another episode of star formation also, because we calculated the star formation efficiency of the galaxy is extremely low, like for 3 to 5%, like 3 to 5% of the gas we have, and only 3 to 5% of that the galaxy is able to convert it to stars. So it's extremely negligible. That one of the reason for that is maybe high temperature in the galactic halo. Circumgalactic halo has is shock heated, probably is in high temperature. That is why it's not able to cool down. Now I think there is an interesting work going on, I think in IUCA or something, like they are investigating the how AGN feedback interacts with the disk gas. So we can get some answer from there, I think, like if it can positively affect the star formation or negatively affect the star formation, in which condition, or both, probably at different time scale. That can give us some answer, I think.
Position of black hole came in from the modulation, right?
Yeah.
So, but then why we need black hole? I mean, can we think about another alternative where we are talking about a galaxy of this scale whose gravitational potential itself is able to create such a huge dispersion?
Yeah.
So, have you evaluated that contribution?
Yeah, I have found out the timescale for cooling for the halo from virial theorem, like what kind of timescale it would require to condense the like galactic circumgalactic gas into the galactic plane. So it seems like it's not possible. I'll come to that later. Now, how black holes can affect the star formation of a galaxy is very, we don't know anything about that. At least I don't know. Like Schwarzschild radius of a black hole is very small, like 3 times mass then divided by solar mass kilometer. For our case, black hole mass is of the order of 10 to the 8. So you get Schwarzschild radius of the our galaxy as 24 kilometers, which is 10 to the minus 16 kiloparsec. So dimension of the disk is 26.4 kpc. So it's huge. So how it is affecting the star formation in the disk is a major question. And recently, Martin in 2018 paper, they found a correlation between black hole mass and star formation rate of the host galaxy. They found that higher the black hole mass, the star formation was going at higher rate at some period of time, and they got quenched fast rather than the galaxies that have lower black hole mass. So how black holes influence the star formation of a galaxy, we don't know exactly how it happens. So also why we can see the black hole accretion, maybe the different infall scenario is happening, like Bondi accretion. when the spherical infall is happening, like no angular momentum transfer in the black hole, so you can see everything goes into the black hole, no radiation coming out of that. So intermediate rate accretion gives us optically thick disks, but physically thin. Optically thick means physically thin, and optically thick means physically thin. So you have a lot of neighboring atoms that can interact. So there is higher possibility of radiation and dissipation. So we can see something coming out of the accretion disk. So nothing. I don't think optically intermediate Eddington rate accretion is happening here. It might be Bondi accretion or advection dominated accretion flow. Like it's extremely low Eddington rate accretion. Nothing is coming out. The disk evaporates and nothing is coming out of the radiation. Or maybe a combination of all that in different time scales. That is also possible. So, yeah.
You said that was around 26 kbc.
Disk, yeah.
Then end to end.
No, radius.
Radius.
Yeah.
Okay, so in total it's like 50.
Yeah. Also, the virial radius of Milky Way is, I think, around 200 kpc. Like virial radius of that galaxy is around 600 kpc. It's almost 3 times. So generally, supermassive black holes reside in galaxies that are generally massive. But we need to find out the baryon now. What kind of baryon composition is that for the galaxy? But because there was a thing that we want to find the missing baryons. Where are they gone missing? So trace them. That was the major question here. Because massive galaxies most probably don't have, like, we expect that they have baryons, but we don't find observation that much baryon. So that's called missing baryon problem. So baryons in generally are, in astronomy, baryons are loosely described that observational matter, like electron is also included in that. But in particle physics, baryons are like fermions that are made of 3 quarks. Like in lepton also is taken into account in baryon in astrophysics. So that has to be taken into account. So generally, galaxy's baryon content is made of stars, gas, and dust. So we find the object has a huge stellar mass of the order of 10 to 11 mson, with atomic hydrogen gas mass of 10 to 11, molecular 10 to 9, and dust mass 10 to 8. So we neglected the ionized gas mass in our composition because there are no, we showed you previously that there are no young stellar populations, so not much UV radiation is coming out. So to ionize a gas cloud, you need at least less than 912 angstrom of radiation. So there is no young stellar mass here, young population of stars, so ionized gas mass can be neglected here. Also, Dye et al. 2012 estimated the X-ray halo mass from XMM Newton observation around 10 to, it is extrapolated up to virial radius about 10 to 11 solar mass. So you can see most of the mass is in the halo, hot halo, circumgalactic hot halo. It is not able to come down to the disk and condensed over there. Okay. I think 10 to 10 is Milky Way, right? 11. Yeah, I have to say.
We say like 100 billion stars in galaxy.
Huh?
100 billion.
100 billion, yeah.
Yeah. So
yeah.
That is very
low. Okay. Sorry? I think.
X-ray halo mass.
Yeah.
Why is it
such a? Yeah. That is why we don't know that. Like it is having a huge extra halo. Yeah. Yes. So we thought that probably that the gas never cooled up and came down to the disk.
But what is the time scale you're talking about?
Yeah, I'll come. Yeah. Yeah, yeah. Okay. So you can see most of the mass is in the halo, X-ray halo, in the circumgalactic halo of the galaxy. Now here, if we plot the, like this is the called baryonic Taylor-Fisher relation, where baryonic mass of a galaxy is proportional to rotational velocity to the power 3.724 is like that. So we don't know why it exists, but it exists. Uh, the more massive the galaxies, I think around mass of 10 to the 10.5, we saw a break in the baryonic Taylor-Fisher relation. Like it's a huge mass range. Every galaxy is following that relation, but suddenly there is a break. So why there is a break? It's a big thing. Like majority of the baryons you can find here for that galaxies. For those galaxies you can find baryons. And one thing we also find when we add the hot halo gas component of other such massive galaxies like J2345, NGC 1961, NGC 6753, all of them goes to satisfy the baryonic Taylor-Fisher relation, but UGC 12591 also still falls far below the relation. So probably most of the mass is still unobserved, or maybe there is some problem here. So we don't know what it is. Sorry? I can. Yeah. Yeah. No, no. That is baryonic mass. Yeah, yeah. Like if you take the baryonic Taylor-Fisher relation to be true, then this galaxy have a baryonic deficiency of 77%. So it's a huge deficiency. So we found mass within the virial radius taking hydrostatic equilibrium to be true around of the order of 10 to the 13. Mass observed taking the hot halo gas into account is 10 to the 11. So baryon fraction is around 0.026, which is far below the cosmological universal baryon fraction, which is 0.167, something like that. The one interesting thing is, like if we take galaxy clusters and galaxy groups, it tend to follow the universal baryon fraction. They satisfy that relation, at least they go close to that. But intermediate scale system like galaxy within the virial radius, they do not follow that. For that reason, we need to know some basic things about galaxy formation. Basically, in the beginning, gas was same distribution as dark matter. Now, due to some fluctuation, dark matter started to clump together, and it decoupled from Hubble's expansion, and then gas were coming and within the potential of dark matter, and it gets shock heated. Shock heating is something when some object is going in the very fast and it gets like pulled back by something else, then shock wave is created, and it's an adiabatic thing. That is change in temperature, like what is it called? Change in heat energy. There is no change in heat energy, so temperature cannot distribute. So some clumps get more heated. So the gas get more heated, shock heated. So and after some time, it gets like dark matter cannot dissipate through like radiation, but baryonic matter can interact and dissipate through radiation. So that is why the gas is condensed into and fall into the gravitational potential well of the dark matter halo, and then there is a galaxy formation. And then gas attains hydrostatic equilibrium. So gas cools down mostly by dissipative radiation and settles into mostly two-dimensional and surrounded by 3D halo. Okay. This is the general, I mean, simple analytic model of galaxy formation. But now we calculate what is the temperature, taking that at 500 kpc hydrostatic equilibrium is satisfied. We can calculate the virial temperature of the gas over there, and we found that virial temperature is around 0.5 to 0.8 keV, which is of the order of 10 to the 6 Kelvin. So, and I think the guy who wrote X-ray paper also found temperature around 0.64 keV from considering X-ray hydrostatic equilibrium, I think. So, this is the gas temperature at halo, and we need to cool it down to 10 to 20 Kelvin so that it can form stars. Now, it is calculated that cooling time in the X-ray halo gas is estimated as 2.8 to 6.3 gigayear with a cooling rate of 0.15 to 0.21 solar mass per year. I mean, if you take some mass, it will take 6.3 gigayear probably to cool it down. So if you multiply these two things, 0.1 probably take the higher limit, 0.21 multiplied by 6.3, you'll get a mass component of the order of 10 to the 9. So what we got is our stellar mass is of the order of 10 to the 11. So in no way it is possible that all the gas from the halo came down to the disk and condensed and made such big massive galaxy. So there are some other processes involved. So it's not conforming with the normal analytical model of galaxy formation. Also, if you can calculate the if you like, probably for simplistic case, if you can take the gas here and center like virial radius, and you can take the velocity, you can in the simplest case you can follow like distance covered into distance covered is velocity into time. So if you consider that time scale, which is r virial radius divided by rotational velocity, that comes about 10 to the 12 year, more than Hubble time. So that 10 to the 11 solar mass galaxy we are not able to make it within Hubble time. So it's not possible. So we disregard that it has formed from some simple galaxy formation theory that we are proposing, like we have been proposing for long. So some other processes may be involved in order to build the galaxy. One thing that comes to mind is merger. So that's the only way. Merger is a big clue here because that is the only way the bulge can get bigger, and also we can achieve 10 to the 11, at least observe 10 to the 11 solar mass. So this is the baryon fraction plot. You can see the galaxy clusters here. These are galaxy groups. This is UGC 12591, UGC 12591, our galaxy, our target. And this is the universal baryon fraction. So galaxy clusters and galaxy groups tend to go towards satisfying the universal baryon fraction, but individual galaxies like UGC 12591 and some non-starburst field galaxies, they do not follow. And there is one galaxy like these galaxies, these are also massive galaxies like J23450449, NGC 1961. They also tend to go towards that universal baryon fraction. So we can find the baryons there, but UGC 12591 is an exception. We cannot find baryons till now. Okay. So our guess is that most of the baryons are in hot halo, unobserved. Probably future more like sophisticated sensitive X-ray mission is necessary to observe that. And there may be other possibility that there. I think someone wrote a paper on finding galaxies in intergalactic medium. Like most of the in today's world, most of the baryons are found in intergalactic medium. I think 40% of the total baryons of the universe. So we need to find that whether we can accommodate for that. Also, how like these baryons go out of the galactic potential well into the intergalactic medium? So that may be interesting question to answer. But I think one big problem here is uh, estimating the virial mass. We are considering that it holds true the hydrostatic equilibrium, like pressure and gravity, like we can balance, but that gives us the virial mass. But suppose it is not true, like suppose hydrostatic equilibrium is not holding, that gas is either collapsing or is expanding, it's like oscillation mode, then we cannot simply apply the hydrostatic, like Newtonian, whatever you want to call, uh, equations there, and that may give us a wrong estimate of uh, virial mass. So there is a problem, so we need to estimate that further, like I don't know how to estimate that, probably X-ray or ultraviolet. Yeah, ultraviolet can, I think, trace that.
The missing mass.
Yeah, like in halo, hot halo of the temperature of 10 to the 7, 10 to the 6, ultraviolet probably.
Yeah, they look into lines usually. If the spectroscopy is available,
Yeah,
they look into lines like output lines and
yeah,
so that basically accounted for much of the missing mass problem.
yeah, yeah,
But then again, critical issue is the flux.
yeah,
So you mentioned about like the possibility of merger, right, or interaction.
yeah,
But then that should leave some effect on the structure, right?
yeah, like that is,
Not
yeah.
seen, right?
No, that I said in the beginning, like maybe the clue is it remains in a very isolated environment, and it has a very high angular momentum. So it may be a like kind of indirect thing about past mergers. Like I don't know how it got so planar structure, because all the things may have like angular momentum coming together like that. So it may come together. Two galaxies may come like that, but it may got such time to stable it down, cancel all the angular momentum components, and only the vertical components remaining. So that is a problem. But the isolated environment may give some clue that it may have sucked up all the thing surrounding that.
The interaction, let's say, drawing the bulbs,
Yeah.
effect of that, like making the bulb bigger, without creating much issue with the base
Yeah.
structure.
Yeah. Yes. Yes.
That is hard to
Yeah. Yes.
manage.
Yes. 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 Yeah. 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 I think coma cluster. Yeah. We have to see that. Yeah. Okay. Yeah. Okay. Okay. So, like, there was other propositions that warm hot probing the warm hot intergalactic medium WHIM, for which temperature ranges from 25 to 27, which is believed to contain much of the variance. Like now, theory tells us that probably it is there, studying the galaxy clusters and all. Also, I think there are another theory called modified Newtonian dynamics, which can probably take into account the baryon deficiency, but we don't know how exactly it works. So these are things we could answer. I think I could probably answer. The reason for huge bulge, probably fast mergers, growth of the black hole, past mergers or accretion, probably intermediate mode accretion, intermediate Eddington rate accretion, low star formation is morphological quenching, AGN activity, and I don't know how much stellar feedback like supernova and all effect in the galactic scale that maybe suppress the star formation in the local scale, but in galactic scale I don't know how it's how much its effect is. So we can find that where could the baryons be, like either within the dark halo or beyond virial radius in the intergalactic medium. This is the constraint here. So we still don't know that activity of AGN, when positive feedback happened, when negative feedback happened. As I told, like positive feedback is when the feedback induce star formation in the disk, and negative feedback reduces the star formation in the disk. So, and another question is whether hot halo gas is exactly in hydrostatic equilibrium or not. We don't know the exactly virial mass. So tracing the baryon completely, we couldn't trace the baryons completely till now, but probably we'll get to that, get there. So, like we are taking with the same object, we are trying to do another work like studying the globular clusters. I think Sija ma'am is there, and probably we will be able to see globular cluster. There is a problem that, like, same question like whether chicken came first. Like, what is that? Like, huh? Egg or chicken, yeah, something like that. Whether globular cluster stars first form or galaxy form first, we don't know that. So globular clusters are supposed to be the galactic fossils. We need to do galactic archaeology there, and we'll probably try to tell the early history of the universe. But globular cluster are supposed to be formed very early, and distribution of the globular cluster within dark matter halo could possibly give us a sense of gravitational potential well also, because we don't know exactly what shape is the gravitational potential well of the dark matter. So that could also we can answer. So all that we discussed, I think in the end of the project, I realized I do not know anything. Thank you.
You mentioned about the dark matter decoupling.
Yeah.
So, would that have created? I mean, have you thought about like the role of dark matter in this?
Yeah, like it has such high angular momentum. So what is preventing it from going like haywire? So there must be some gravitational dynamical friction going on there, but we don't know exactly whether dark matter is co-rotating with the galaxy or what. If it is stable, we don't know exactly that.
Because that is where the possible X-ray analysis, like people did for blood cluster and all that. Like, do you see something interesting with the X-ray halo, like any properties of X-ray distribution in the halo?
Okay.
Any stickiness or bimodality or has somebody reported that?
I don't.
If that is the case, you're saying co-rotating, you will
Yeah.
definitely see
Yeah.
traces of that in the X-ray distribution.
Yes. Yeah, we can do some spectroscopy there. I think in the globular cluster case also, like if I can do spectroscopy and find out in which direction globular clusters are moving, and from that, globular clusters can be embedded in the dark matter halo, right? So from that we can probably get a sense about what kind of distribution is there of the dark matter. Yeah, spherical symmetric. Yeah. Yeah.
Also, you have mentioned like it's published in MNRS, right? No? So, combination of the published work is
So when you were talking about the decomposition part, you mentioned about the pseudo bulge. Is it present in the galaxy?
The pseudo bulges are like those bulges that are not very spheroidal in nature. Like it's
when you define or show the pole with from galaxy,
yeah.
you mentioned about
Pseudo bulges are those bulges that have Sarsic index less than 2.
you don't have a pseudo bulge.
No, no, here. In other galaxies, like I show that jet spring galaxy J2345049, that has a pseudo bulge. But one thing is that galaxy has a jet, I think 160 kpc in both direction, but this galaxy has no jet. But they both are more or less showing the same properties, like low star formation rate and all.
One more thing, when you showed the star formation rate
Hmm.
from Shankar Ray and Maxwell,
Hmm.
it was twice compared to Shankar
Yeah,
Ray.
yeah.
But out this
Yeah.
more
Yeah, yeah.
twice.
Yeah.
So what could be the
Because they take into account different stellar star SSP, I think, what is the full form? Like star population synthesis models and Chabrier models, I think, or IMF is different. Or
you can define it, right?
yeah, I can define it, but by default, I think McFIS uses IMF1 initial mass function and CL use IMF is 0. So there might be some, like I think they are in within the error bars of each other. Yeah.
You know, and one corresponds to either Saltine or Rupa.
Yeah, yeah, and Chabrier. Yeah.
But if you define same thing
Yeah.
for Shankar Ray and Maxwell,
Yeah.
will it give you the same? I'm just asking for.
Because like both the codes are differently written, so like the logic may be slightly different, that is giving rise to some distribution, like probably in 1 sigma or 2 sigma confidence interval, it is probably the same.
One more thing.
Yeah.
About AGN.
Yeah.
So you were confused whether it is a positive or negative.
Yeah.
Right? You are seeing a reduced formation.
Yeah.
That definitely means a negative.
Yeah, negative agent, but we are seeing also a huge stellar mass 10 to the 11. So some point it have.
He's saying like if I evaluate that over a period of time, is it like when would the switch happen? Is it like positive at some point, negative at some other point?
Have you looked at star formation history that
Yeah.
from Saltine? Sorry, Shankar Ray and Maxwell.
Yeah.
They give the star formation history, right?
Yeah.
You will get for 10 years, 50 years,
Mm.
100 million years. Sorry.
Mm.
So did you check with that?
Yeah, there is no change.
No change.
Yeah. So that is why I said like for at least 10 to the 8 years, 10 to the 8, yeah, 10 to the 8 years, the galaxy is quiescent probably, because before that there might be some gas outflow in the circumgalactic halo, and this is taking time to cool down in that. Maybe after some time we'll again see some star formation happening. Because yeah,
Interaction you have mentioned happened before 10 to the 8.
at least.
So if that's the case,
Yeah.
are you expecting a multiple local cluster system? So what I understand is like there should be an interaction. The local cluster system should be both 6 to 7 gigayears range, right? No, initial system will be in the level space and there will be a gap. Then
But local clusters, they may not be forming a just coming. So it is not be used.
That we can check for 2 and
we can expect that it is 2 or 3 different populations.
yeah, how much big is this X-ray halo compared to the diagram?
I think it's they detected it up to 80 kpc, but from
Time.
sorry,
It detects how much is this?
sorry, I can.
Ratio. If this is X,
Yeah.
how much is this?
This is okay. Like from center, it is extrapolated up to 80 kpc, I think.
25. That's 3 times.
Yeah.
I know this. Like this galaxy you mentioned quite often.
Yes. Yes.
So like we're seeing a lot of similarities.
Yes.
Master, it has like even NASA has a high rotation.
Yes.
So like and even both of them are actually coinciding with red cloud and the blue cloud. So actually
Yes.
like
Yeah.
so
Yeah.
are you like looking at something very similar or is it like there are some different?
Yeah. We are like we discussed it before. Like they are going in the same direction, but with different processes. There is a jet, and in the galaxy there is no jet. So they are following different evolution process, but their final result is the same almost. So that is a question.
back to one or two slides back where yeah, here that green symbol is spiral.
Green spiral galaxies.
Yeah, because it's very surprising that it is falling below the green. So what is the reason? Like if it is a lenticular, if it is somewhere above spiral means mostly it is lower than mass of, or is there any peculiarity for those spirals? Did you check that?
I think Lie 18 spiral galaxies. They are. I don't think they are super spirals.
Yeah, so
Yeah.
it is mostly surprising, right?
Yeah.
Not
Yeah.
below that, right? That is coming below
Yeah.
for this particular one.
Yes.
Than spiral. So maybe you can check it like
Yeah.
which all are nearly monthly enough
Yeah.
in comparison to this, and also maybe some are isolated
Yeah.
galaxies
Yeah.
that you
Yeah.
include in this one. That may be one of them.
Yeah. Also interesting that galaxy clusters and galaxy groups almost go towards the universal baryon fraction. So one thing could be that within the virial radius, the gas have gone out out beyond the virial radius, or in the first place from out of the virial radius, they never came within the virial radius. So that could be the problem.
So I would like to take this opportunity to thank Shankar for the wonderful talk. Thank you, Shankar. I would also like to thank everyone who talk. We'll meet again next week, same time here, and we'll have Rebecca giving the talk. So thank you so much for all. Thank you.
Thank you for the left.
Thank you.